Thank you very much. I'm very happy to be here. Actually, I'm based in Berlin, and I flew today just to join this special event and to meet you all. So very looking forward to all the questions that you have, and yeah, let's get going. So yeah, what I'm going to try today, it's about really kind of challenges and learning. So it's less about kind of what to do, but maybe more kind of a personal experience that we have lived to trying to measure to optimize offline marketing campaigns. So this is a brief outlook of the talk. So I'm going to talk about a little bit about the motivation behind what we do, and kind of the rest of the presentation, we're going to generate a synthetic data set because these things are very hard to measure. Or in order to grab some concepts, it's always useful to run some simulations, or you can actually control the truth and play God, so to say. And then we're going to go through various type of techniques which can allow us to get estimations on media efficiency effects, which of course can be applied to other domains. And at the very end, I will finalize with some remarks and takeaways which could ideally trigger some discussion. So the motivation here is that very recently, let's say, given the kind of privacy settings and kind of the need to really optimize and not kind of waste money in marketing, many companies and many famous cases have kind of popped out there saying that kind of through this digital era where everything was cookie based and kind of depending on attribution models, actually there was a bad decision regarding to investments. So for example, Adidas presented a quite nice study saying that they, let's say, based on a kind of alternative econometric method, that they were overestimating in a performance marketing. And whereas kind of a lot of their sales were actually being driven by brand. So they were, yeah, wasting a lot of money, but of course they now know and probably are correcting that. And there are other cases, for example, eBay, which turned out like around 200 million euros in digital, and actually nothing happened. Actually, it happened even more that they put that into different channels and their sales actually went up. So this is actually very crucial for companies. And understanding how to actually optimize and manage this budget, I mean, because we're not talking about a couple of euros, of course, it's really key. So usually how people are working out these days about how to manage the holistic marketing efficiency is through kind of major components. One of them is what we're going to talk today, which is about A/B testing and experimentation. Of course, there's the attribution model, which is kind of very kind of appropriate for digital channels. And there's something in between that is called a media mix model, which is trying to link these two together. But actually, it's not that one links the two, but also they're interconnected. Because as I will mention, actually input from the geo-experiments can actually be fed into the media mix model to kind of calibrate that for measurement and optimization purposes. So we are actually working these 4 components ourselves. And we, for example, are building an MMM, a marketing mix model in-house. And the key idea here is to actually look into the data from a statistical point of view, where we actually can track other channels like TV, podcasts, radio, which is actually quite hard to track. And we're actually going to draw conclusions regarding efficiency through a statistical method. And this by itself could be yet another meetup. So here's an idea for it. But this is not what we're going to do today. What we're going to do today is to talk about geo-experimentation. So this is actually pretty tricky. So what I decided for us today is to play a game on which we are going to generate a data set which should resemble very closely to what you will encounter in a real kind of campaign analysis. And then we'll see, let's say, techniques which can allow us to kind of recover this. So I invented a city where I have 40 zip codes, and I created a treatment and control. So the treatment is blue, and the treatment is red, and the control is blue. And what I did was to simulate orders. And one thing that you see, I mean, the math is there, it's not very important, is that I allowed this kind of being sampled from a distribution. So there's unknowns that we cannot control. But let's say heuristically, we're going to say that our orders are going to depend on the size on the zip code. If there are more people, probably there are going to be more orders. There's going to be a seasonal component as well. So the weekends that we're going to have more orders. And then we're going to have a base conversion rate, which it's just there because previous campaigns or kind of organic growth. There's going to be a component. So orders are naturally going up. And there's going to be this interaction effect, which is actually the 0.07. Again, the value is not very important, which is actually a contribution that the treatment group is going to be, let's say, seen through the campaign. And by campaign, we can believe, okay, we run certain offline campaign, let's say radio, or we did some direct mail, like say flyers, something that we cannot easily track. But we're going to make this a little bit more interesting, and we're going to assume that each zip code has a strength feature which we cannot see. And let's say it's about market penetration or maybe affinity to the brand, which maybe you cannot measure, but it's there, and it's definitely going to affect your conversion rate. Or if we see the order rate, let's say orders divided by population, we see that the control and the treatment groups actually differ. But most importantly, I made this data set in such a way that just the treatment group has a higher strength. So the groups are not very comparable. So there's an unobserved component there that is gonna kind of bias our results. But the beauty of it is that we're always gonna have these unknowns. We need just to understand how to deal with that. So through the presentation, we will see this type of diagrams, which is a DAG, a diastatic graph, which kind of describes how our model and how we think about the quantities that we have there. So for example, we have the treatment seasonality and the population affecting order. But the tricky part is that strength, this unobserved component, affects both the treatment, because just the treatment has high strength, and of course the orders through that formula. And the question is always about a campaign analysis, whether what we seen as an uplift actually spurious or given because something else, or is it's really a commercial statement. And this is again a huge field. But what I want to emphasize here is that, let's say for the kind of this example, we're going to be interested in the average treatment effect. So let's say the average difference in orders over the treatment and control group. And let's say one way of doing this, let's say very simple, it take the orders in the treatment, take the orders in the control group, let's say take the mean and see the difference. But this is not going to give you any causal statement, because you need to ensure that these groups are comparable. So the formula is not very important, but when you take this type of statistic, just by taking like comparing the mean across these two groups, actually this could be because of spurious correlations or confounders, but not really because of the campaign. And this is something that you want to understand. So what you measure, and this is the notation kind of why not and why one, this is in the context of what is called the potential outcomes, is that you need to make sure, or let's say hypothetically understand or verify or assume that your treatment without the, let's say the treatment group of the intervention would have, let's say, developed in the same way as the control group. But if they differ, of course, then the uplift that you will measure will come from something else. So causality versus correlation, this is a big elephant room, which I'm not going to go deep into that, because we're going to go a little bit more pragmatic. So as we know, the data generation process, we can do something very simple. And I can do the same, let's say, exercise, and I can turn off the campaign in the treatment group. I can do that. I just put that to 0, and I just compute the orders. And you that if I do this, then let's say in the campaign period, there's going to be around 5.2 increase on the number of orders. So this is kind of the truth that we can recover. But something interesting to see is that this is observational data. So this is kind of a static campaign. But we can play God and actually run this 10,000 times. We can actually run 10,000 and see that our model specific, let's say the uplift is between 5% course, we don't have information about this one. We just have information about this one. So it's also important to realize that the campaign realization of kind of this intervention. So ideally, what you would like to do is to actually model the whole data generation process, meaning you have a model for your orders and you have a model for the order rates, and one can really do the kind of a generalized little model. And if we know and input the perfect specification of the model, you see that we get a number very close to 0.07, which is the kind of treatment effect that we put by hand. But in the formula, we actually have the strength variable there, which we have in our data set. But in reality, you don't have that. So if you run the same model, the generalized additive model, without strength, you're actually going to get a much an effect, more than like 3 times. So this means that going through this approach, which is the ideal case, can be sometimes, especially if your process is actually quite cumbersome. So what we're going to do, instead of going this way, is we're going to work in what is called, for example, a geocentric model, which is not correct, but a kind of a linear approximation, so that we kind of avoid this type of challenges. So let's go again to a marketing manager. Our marketing manager ran this campaign, and let us assume, for the sake of the exposition, that they were too busy and they did not have a control group. They just ran the campaign. They just spent the campaign in those ZIP codes, and they just want to get some efficiency metrics. So here what you're seeing is actually the sum of the treatment group before and after the campaign. And as you see, this is a very beautiful case. In reality, the signal is much smaller, but for the sake of this position, this will serve. And if you actually, what you would do is take, let's say the campaign lasts a month, take the month before the campaign, and take the relative growth. And if you do this, you're gonna get around 7%. That's great. But here there's something tricky, and this is one of the biggest problems when doing this type of analysis, is that there's a naturally trend component, which we are not taking into consideration. So we are attributing part of the growth to the natural trend component that we're seeing. So we're always overestimating the effect of the campaign, which for the marketing manager may be something good, but if you want to optimize for that, actually you want to be careful about it. So in the case on which you don't have any control group, you can actually do something slightly better. So what you can do is, for example, instead of just comparing the pre and post campaign, we've seen that the problem is precisely the trend. So what you can do is to train a relatively simple time series model, which is based on weekly seasonality, because you see it from the data, and with a kind of local linear trend, which goes up. And this is this type of approach is actually commonly known as Causal-Impact. And I mean, Google has a really nice work and package about it. And we're actually doing is actually passing this intuition that we have to the model, saying we believe there's going to be a weekly seasonality, and we believe there's going to be an upgoing trend, and your estimate here actually still inflated, but it's less than the 7%, around 5.8. And just a bit of a warning, this is the uplift with respect to the seen order. So I guess this makes sense, but in practice, the challenge here is like how to specify the time series model, because you don't want to kind of attribute noise to the campaign. And this is something that we enforce and try to be very emphatic about, the fact that we need to care about the uncertainty. So the point estimate is nice, but it just telling you a very little portion of the story. And something that we also learned is that uncertainty is very valuable. Even if it's big, then we can actually make better decisions just by trying to give everything or reduce everything to a point estimate. So let's say you have a city like Helsinki, where you have been running for years, and then let's say you have a kind of nice expansion for the trend, and especially for the seasonality. Summer is definitely different than winter, and the behavior of orders is quite different. So if you have a long time series, then you can actually model the seasonality. But what if we actually start running these campaigns in new cities where you don't have historical data to actually fit this time series model? So this is simply not going to work. There's one way to actually pass prior knowledge to a forecasting model, meaning you could, for example, take data from, okay, here's going to be my Finnish geography, from Helsinki, and then if you have Tampere as another city where you don't have enough historical data, then you can transfer the seasonality because you're going to assume that it's going to be very similar. You just are just going to gauge that with respect to the orders there. But this is actually quite not straightforward. So I would say a better investment would be actually sync with the marketing manager or with the team and say, let's try to find a control group, because like say having a control group will allow you to kind of take less complexity from the model and pass that to the control group, because if your control is good enough so that it could explain the trend and the seasonality, then you expect that by controlling for this other group, you're going to get the uplift. So this is a common approach and the idea behind the time-based regression framework. And you have a lot of geos. Actually, you can have many of them. In our case, we have 40 zip codes. And then you can kind of pick or do a kind of a study to see if there's any combination of geos which actually serve as a control. And what you would like to test, or like the assumption of this model is very simple, is you're going to test to see if there's a pair of geos, let's say the treatment and control, on which they are related by a linear combination, which means one is a multiple from the other. And the intuition there is clear. You want to make sure that the trend and the seasonality are there. And then once you have that treatment group, then the approach now is rather simple, because instead of having a time series model to train, you can just train that your favorite linear regression. So in this case, just because of the example is nice enough, actually you can just take the sum of all of the zip codes, and then you see that in the pre-campaign phase, actually this is just the data at scale. They look quite fine. You can of course run your favorite statistical test, and then you see the purple line is what you've seen, what you will get from the control group, and then in the green line from the treatment group, and you run a linear regression. And at Wolt, at least in marketing, we really like the Bayesian approach because we actually care a lot about uncertainty. So you can get these type of results on which you have now this simple linear regression, but you can again estimate the prediction intervals. And actually you can do many things within the Bayesian settings. So for example, you can weight the recent points more, for example, if there's the need to, maybe if the relation is not entirely linear, and you actually can constrain your computation based on certain, let's say, domain knowledge, so to say. And in this case, again, we're interested about the cumulative effect, and yeah, it's around 5.7. I mean, not very different from the Causal-Impact approach, and it's no surprise because it's rather simple. This is just, again, controlling by the trend and the seasonality, but using the test group. One other approach which can be very handy is what is called synthetic control. And remember that in the previous example, we have to kind of see which geos would work for control. So sometimes you have certain constraints for the business and you just have a couple of them, but maybe you have a lot and you don't want to kind of run over all the combinations and actually kind of overfit on the selection. So what you can do is actually take all of your available geos and use kind of what is called a convex combination of that. So the intuition here is that if you want to run a regression, you are often actually extrapolating from your training data. What you're going to do here is actually use all of your zip codes, in this case, to generate what is called a synthetic control. And this is going to be kind of what you are going to compare against what you got from the true value. So the recipe is very simple. You take, as the training said, all the historical data in the pre-campaign of all your zip codes, and you train a linear regression with a constraint. And the constraint is that all the coefficients of this linear regression, which in this case you're going to have 27 because you have 27 zip codes in the treatment group, should be positive, and they have to add to 1. And in this case, you're actually not extrapolating, but interpolating. And that actually works quite well in practice. And again, there's a Bayesian way of approaching this so that we actually get the appropriate confidence intervals. And actually, because of the nature of the approach, we're going to get the support. Let's say this regression is going to capture just the most important zip codes, and it's less likely to take a big combination of those. Of course, there are actually many variations about this. We have also work from Google on trim matching, which is not really synthetic control, but they have a way of selecting these geos based on certain requirements. So for example, if you want to detect certain uplift in certain specific metric, you can put that into this. There's algorithm to do a greedy search, which can be very efficient. And we have a meta geolif, which actually runs on something very similar to synthetic control. I didn't want to present this approach because, again, sorry, the geolif from Meta, just because I wanted to just be more transparent about what's happening behind the scenes. But of course, if you maybe don't have that capacity, there are existing solutions for that. And let's say people let's say coming from economics see that actually there are very kind of different methods and different flavors to estimating this type of effect. One of them, which is very common, it's called difference in difference. And this is a little bit different and it's less about predicting and about kind of looking to the what would have happened, which is the contrafactor in the time series setting, but trying to do this for all the zip codes. So in this case, we're still we are assuming that we have all the zip codes for the train, for the control, and all the zip codes for the control. And what we want to see if, for example, the uplift, like in the pre-campaign and the post-campaign analysis in the post-campaign period, actually if this uplift is somehow consistent. And there's a big assumption here, and this is where kind of all of the kind of framework about causality comes into the place, and is that you're going to assume that the growth, and I will show that in a plot later, of the slope of the control group is somehow is similar to the treatment group if they had had no campaign. And that's very key because otherwise you would be attributing the difference to something else. You can actually estimate this in a very simple manner. It's just a linear regression with an interaction. Yeah, the results are actually here around 5.4. There's kind of a little caveat about this estimate, but it's not really important. But as we can play God, we can verify the assumption. And in this case, actually, the condition of the difference in difference does not happen if I turn off the campaign, but the difference is not that much. But I guess what is important here is that the intuition behind difference in difference is that you're going to compute the pre and post for both treatment and control, and then you're going to estimate the what if had happened in the treatment without the treatment group without intervention, and just estimate the difference. What I like about this approach is that it's very easy to interpret, it's very easy to explain, but it has a very strong requirement, which is this parallel trends, which there's no way you know that. You can, of course, what you can do is actually test this before the campaign and see if this somehow holds true, but this is a big assumption that one cannot underestimate. And the last kind of approach that I want to just briefly talk about is something that is called panel data and fixed effects. And if you think about it, we haven't used the fact that we have many observations for the same zip code. And that's very valuable information. Say in most of the other approach, we've aggregated this data, which potentially we have, let's say, lost a lot of information. So in the panel data and fixed effects approach, we're actually going to use the whole data set. And what we're going to model is the orders, where all the log of the orders, if I want to look into the incrementality of a fixed effect regarding the interaction between if there was a treatment and if it's part of the campaign. And I'm going to have individual intercepts, this alpha I, for each zip code. And I'm going to have also control variables for the time. So in essence, this is a cleverly linear regression where you can kind of see, like, heuristically, what you're doing is taking a dummy variable for each zip code But of course, if you have a lot of zip codes or a lot of users, this is not going to work. But it still works just because you can do the estimation in a two-stage regression, on which this kind of what you actually do is to take the mean over the individuals, let's say the zip codes and the time component, what is the meaning the data, and then you can make this work. But there's something very nice here, and is that once you fit this model, you actually can compare the fixed intercept for each zip code. And notice that I'm just using information from the treatment and about the campaign. And what you see is that this intercept splits in two groups, and they split precisely in the strength variable, which means the panel effect, the panel data and fixed effect has the advantage that it will just destroy or kind of take into consideration all of unobserved kind of variables, which are constant over time, which is very, very powerful. So here in the lower plot, you see the orders against the population of zip code, and here you see the difference between these two, and we get something very similar when you do this. And this comes very handy because of course you don't know when you're modeling, but when you see such results, you still get some insights from your experiment, which is something that I found very, very interesting. So I know that was a little bit too much, but the message is the following. I have various takeaways, and I'll be happy to chat about it. So first of all, it's very important to measure if we want to optimize. Like, that's key. The second is that measuring is hard, and that's what makes this fun. And this is actually a very kind of active developing field, especially it's kind of a new trend in what we call data science. So some tips is from what we learned is that I know sometimes it's hard and money comes quite fast, and maybe people want to go through campaigns, but let's say working with your team and trying to find a control group to measure it, it's a good investment. It will pay off, and there's going to be a work to be done setting up the experiment, but it definitely pays off. The second is that that you need to roll the DAG, which means like be conscious about the assumptions that you're making. Don't just throw everything to a linear regression. It will most likely fail. What my advice and what and not mine, but from people that actually are experts in the topic, is really draw your assumptions, because your results are going to be based on what you believe. And there's no God or there's no simulation that will give you this, but it's your domain knowledge. And I think writing these effects and writing this diagram is very, very nice, especially if you do it together with stakeholders. So another one, which I think is maybe the most important one, is simulations are very powerful. Every time I have to do something new, instead of doing the math, in spite of the fact that I spent a lot of time there, I actually write a simulation, and then you can test whether the approach is going to work. Because if you have such a situation, and you're wondering whether you should use difference from differences, or maybe actually, see whether, say, up to which extent this Causal-Impact approach can bring good results if you don't have a control group. You don't know that a priori, but by simulating and, for example, by increasing the noise, you can see how much this estimation will differ. And this is something that has saved me a lot of time. And yeah, uncertainty quantification is also very important. So please don't stay with point estimates. And the last one is learn and iterate. And I think this is actually part of the journey that we're having at the moment. And yeah, thank you very much.
Thank you. This was really amazing. Thanks for all the simulations and comparing the techniques, discussing the advantages and disadvantages. So do you guys have any questions? Yes.
Thanks. Joona from AWS. Would you go about gathering a control group? Or actually, well, how do you go about using a control group, getting one, and so forth?
So let me give you an example. Let's say you want to do. I should have studied more geography, but let's let's say you want to do like the same experiment in Helsinki.
Yeah, okay. Yeah.
And maybe you are going to give a direct mail, or like put some flyers. So most likely you are going to be in the surroundings. So you don't want to make it really random. So in that regard, there's going to be difference in the zip codes. Maybe your control group would be maybe ones where your brand is already quite strong and the treatment is not. It's not perfect. They're not perfectly comparable. But what is important is for you to know and distinguish which could be the potential confounders and see if you have data for that. So for example, if you have a very zip codes, which are very different in the area regarding like zones, but maybe a control variable could be the number of actually restaurants which serve there, and that will control on this kind of penetration or strength of the brand. So for example, if you want to test about if smoking is dangerous for women which are pregnant, you can just not run an experiment, right? Like you could, but it's not ethically correct. And in the industry, it happens something similar. The business constraints, which kind of constrain the selection, but as long as you try to really understand these unknowns, hopefully, you can still make it work within the space more of causal inference.